think you should start. You might be late for 15-20 minutes.
Ah, okay. Okay.
This time.
Okay, good. So if you have already filled the form, I circulated.
Yeah.
Okay. Okay, so good morning, first of all. My name is Stefano. Thank you. So you already know my name, Stefano Salon. I work at the OGS. So usually the first lesson is a little bit introductory. So I know that two of you, so you are from the Gabriele and Alessandra, so you are from the PhD course, and the other one are from the Diploma. Okay. So I work at the OGS. Everyone does know OGS? No? Okay, so OGS is the National Institute in Italy for Oceanography and Applied Geophysics. Okay? And I am part of the oceanographic section, and more specifically from the modeling group. Okay? Which actually we have our rooms in the ground floor of the former CISA building. Okay? So just 2 floors below the ESP section. So it is, I think, maybe this is the 10th year I do this course. So at the beginning, I did it only for the PhD program from the University of Trieste. So the PhD program in Earth Science, Fluid Dynamics, Earth Science, and Mathematics, which 2 of them, more or less, is like that. The denomination changed a little bit in the last years. And so initially this course was standalone, but there was some problem during the, let's say, couple of 2 years ago, since it was done in the second semester. So some students find some topics that were, in some sense, was already done in previous, or touched at least in previous courses. So together with Riccardo Farnetti, we decided to merge his course and my course in order to have this very long course, which is 18 lectures. So you already finished the first part, okay, from lecture 9 to lecture 1 to lecture 9, and now this is the second part. As you have seen, the schedule is pretty tight because this year we wanted to finish very earlier, before Christmas, actually, and the idea is since I didn't have enough time to organize the courses, we decided to shrink very much the second part. So I think the second part of the course is a little bit easier from the mathematical point of view. But it's important for you to follow. I will give you all the information because the course is strongly based on a book, which is a book by Cushman Rosen. I will give you all the detail later. And I quite strictly follow the PDF. Okay, so there is I think 1 or 2 copies in the library, but I will give you the PDF, which I downloaded maybe 10 years ago, when it was still, let's say, free on the web. So, and it's a very nice book, very, very nice. So very, let's say, didactic, very propedeutic. So the first lesson is a little bit more relaxed than the other one. So my work is related to operational oceanography. So I present myself, and then I will give you some minutes to present yourself. So I work with a big program, European program, which is called Copernicus. So Copernicus is a very big European program which deals with climate change, with land security, with ocean sea security, and with marine environment. So in particularly, I work within the marine environment, and with my group, we provide the products for the biogeochemistry of the Mediterranean Sea. So we solve, let's say, the chemical equations which try to represent the chemistry in the ocean. Not just the inorganic chemistry, but also the organic chemistry. So things like nitrate, for example, or chlorophyll, or carbon fluxes, we solve and make some sort of forecast. Okay, so like the weather forecast, but for the ocean, and not just for the physics ocean, but for the, let's say, green ocean. Okay, so if you want more information, you can Google Copernicus.eu, or you can look for Siemens, okay, which stands for Copernicus Marine Environment Monitoring System. Okay, now finish. You can find more things about what we do on the OGS website. So I will ask you very brief presentation from you, so your name, and which is your experience. So which is your master, how much you know about meteorology or oceanography. Okay, so let's start from the yes, everyone thinks that we start from this, but we start from that. Okay, please.
Amazing. And I have a degree in meteorology, climate science.
Okay. Okay. So you already have an experience, or just studying? So you work a little bit on.
Maybe for attachment for like maybe 2 or 3 months.
Okay.
In a semester.
Okay. Okay. So meteorology, very good.
My name is John Michel. I'm from Cuba. I have a bachelor in meteorology.
Okay. Very good.
I'm Alessandro. I'm a PhD student here in Jesse, and I have a degree in geology and geophysics.
Okay.
My name is Tam. I'm from Vietnam. I finished master in mathematics and mechanics.
Okay.
My name is Mallasa. I'm from Ethiopia, and I studied solid earth geophysics in my master's.
Okay.
My name is Apsara and I am from Nepal. I did master in astrophysics.
Okay. Good.
It's totally
My name is Lydia. I'm from Guatemala and I have a bachelor in physics.
Okay.
My name is Gabriele. I'm from Italy, and my degree is in mathematics.
Okay. So it's pretty spread the experience. So good. Very good. So for some of you, most of the thing will be, I wouldn't say easy, but something that maybe you already, if you read or you already, if you already read the program, I think that those of you who studied mathematics already knows, for example, what is the Ekman layer. I think so. Sorry, not for mathematics. So those of you who study meteorology, okay. So, but those of you who study mathematics, for example, know something about, let's say, instability. So the notion of instability, okay? So, or for example, FD, which stands for fluid dynamics, okay? Or of course, equation. So some of the words that are spotted here in the program can, for some reason, give some hint about the fact that this course, exactly like the first part of the course, which was in fluid dynamics, is a sort of a mixture between mathematics. Of course, mathematics is at the foundation of this course, so that's why even in the past, all the people who followed this course from the PhD or for the diploma course who had background in mathematics didn't have any difficulty to follow it, to understand. But the thing that is a little bit more specific of this course is the fact that we have the word geophysical. So geophysical means that we have two specific aspects of the fluid dynamics, because of course FD stands for fluid dynamics. So the word geophysical stands for the fact that we have two characters that play a very important role, which are, okay, maybe this is, I would like to have a sort of active lesson, so I don't like to speak for 1 hour and a half without having anything like a feedback. So for those of you, but also for all of you who had some idea, so which are the two important, let's say, forces or effects which are included in this geophysical word? So something that relates the fluid dynamics with the geophysics. It's a body forces. Okay, so what kind of body forces?
due to gravity.
Yeah, it's related to gravity, yeah, okay.
in this course?
Okay, one is gravity and is stratification. Okay, so the fact that we do not have, like possibly quite common in fluid dynamics, homogeneous flow, but we have a stratified flow. Okay, so flow which is a little bit dense or a little bit heavy. The other very important thing is that what is the other link to the geophysics? Rotation, that's great. Astrophysics, okay, so for you, it's pretty easy. Okay, that's great. So the rotation and stratification. So as I tell you before, this is the book. This is during the course, but I will give you this afternoon, as soon as I will have your email, I think. Yeah, in case that John one came, please forward him the link. So there are two copies, two editions. The first one, I think both of them are present in the library. So I'm very proud to have one of these signed by Benoit Kouchmar-Wazen. And in the ICTP library, I think there will be a couple of them. And this second edition is even more interesting because it has also numerical aspects. So every chapter is also, let's say, completed by some sort of numerical application of what was explained in the chapter. So it's very nice, I like it very much, and I think it's a perfect text for introduction in geophysical fluid dynamics, because geophysical fluid dynamics, you can understand that it's extremely large. So, just to continue, we have three questions that we want to answer today. So what are the topics of GFD? Why we want to study GFD and how we will study GFD. So let's start for the first. So what are the topics? What do you think? What we are going to study in GFD? Come on. It's it's not a quiz. Huh? So even if you give a wrong answer, it's part of the course. So don't be shy. What we are going to study? The meteorologist, what do you say?
Forces of motion.
Forces of motion. Which phenomena? Which are the phenomena that we are going to study, or we try to study? Typical phenomena of the atmosphere, typical phenomena of the ocean. Cyclones, maybe? Okay. Currents, maybe? Okay. So these are three pictures taken from the internet. So this is a vortex street near Canary Island, as seen from the Terra satellite. This is the drop of water going down in a reservoir of water, and these are clouds over mountains. So according to you, in these three phenomena, which are the phenomena which are not part of GFD? I'm just going by intuition, huh? So then we will give some rules, let's say. So this or this? Geophysical fluid dynamics. Geophysical fluid dynamics. So is this something related with geophysics, according to you? Okay. Is this related to geophysics? Yes, but I wouldn't say no many. Okay, you are correct. And this? No. Okay, you're right. Okay, so we can say that this one, of course, this is of course not, because we don't, I don't have an idea, I don't need the rotation to understand, and we will understand, we will see why. This is somehow at the border, okay? So you were right, because most of you were like this is like this, and this is like this. Okay, that's good. Okay, so geophysical fluid dynamics study atmosphere, and studies the cyclones, for example, the general circulation of the atmosphere, it reached to some specific dimension and time scale, as we will see later. And also, of course, it studies the ocean because it's fluid dynamics. Okay, so fluid, of course, gases, liquid, and the first one was a picture taken from the satellite, of course. And this is a picture not taken from satellite but produced by a model. Okay, so we are thinking that we are looking at the tools that GFD are quite diverse, because at the end there was a very nice interview. I will send you the link, given by an Indian scientist who is working at NASA and was host here in the ICTP a couple of years ago during a workshop, who said, why do we use models? Because we have just one Earth, so we cannot do experiments over the Earth. We can just create synthetic Earths and hope that our synthetic replica of Earth are enough, let's say, precise is a little bit too big as a word, but let's say accurate or close to what happened on the Earth, which is, as you might understand, very difficult, because the capacity of a model to work with, to represent all the process in the Earth system is extremely, extremely difficult. So this is a picture of the global circulation of the ocean. So you can see here, but also in the other picture, that you can look at different phenomena. So how we can define phenomena, like in this case. So if I would like to define a phenomena, let's say a character of this picture. So you can see here, okay, there is the Earth, okay, Africa in this case, South America, Europe, Middle Asia. So we have very big characters, very big phenomena working here, okay, and very small, like this one, like this one, like this one, and even smaller, like this one, okay. So we can say that we can take a sort of scale, okay, and this will be a very important concept. So scales of phenomena, in this case spatial scales, but also time scale, is what we can use to identify the phenomena of GFD. And we will see that only the phenomena which will have scale larger than a specific dimension and time scales longest than a specific dimension will be considered in GFD. Similar thing here. So we have large areas which are not. This is, I think, the. So the other picture was, of course, a picture of clouds. So in the visible, okay, in the visible band of the satellite. So we were able to see just the contrast between the area free from clouds and the area with clouds. In this case, this should be related to, I think, currents. So here we see with the colors, so where the colors are blue, there we have low currents. Where the color starts to go to green, yellow, and red, we have strong current. Okay, so even here we can see that we have the area which are, let's say, very homogeneous, and area which are very heterogeneous with very small character, very small phenomena. Okay, and if you may see that the typical phenomena that you have in the ocean are this one, which are called, any one of you? Eddies, okay. And the typical phenomena that are in on the atmosphere are things like this, which are called cyclones. Okay, and you can see, even if the two maps are a little bit different, but look at, for example, this phenomena here, this cyclone, or let's say depression here, and these small eddies here. You can see that the scale is very different. Okay, so just by intuition, just by looking a couple of pictures like this, we can have a lot of information. Okay, just without making simpler consideration. So the typical scale of the phenomena in the atmosphere is larger than the typical scale of the phenomena in the ocean. Okay, this is something that we can grasp from just the analysis of a picture like this. But of course, GFD is not just study of, let's say, the instantaneous phenomena. We saw before a picture from satellite that help meteorologists to make weather prediction. So weather is like a snapshot of the atmospheric system, atmospheric status, and also the other picture. Of course, we cannot take. Well, we can take some picture of the ocean. It's a little bit difficult, more difficult than the atmosphere, because you cannot. I mean, from satellite you can see the entire, the whole air column. Okay, you can of course go directly and penetrate within the atmosphere, but you cannot do in the ocean because electromagnetic waves do not propagate efficiently in the ocean. That's why what we can do from the satellite, from the space, is just to look at some very narrow layer over the ocean surface. Okay, so we can have information about the sea surface temperature, the ocean color, which is something we work with. So ocean color is exactly what the color of the ocean is. Beautiful if you think about it. We can have an idea of winds flowing over the ocean. You can have an idea of the sea level anomalies. Okay, so the difference between the reference anomalies. And these are all, let's say, snapshots from the atmosphere and from the ocean. But of course, GFD, especially in its, let's say, aspect of Earth system modeling, is very useful also to study climate. Okay, so climate is sort of extension. So we are going to extend our time scale, our point of view, and we like, of course, the group of Filippo Giorgi, where most of you are studying now. People are involved in creating models. So most of you, I think, if you are going to stay here and to finalize your, I wish you to finalize your diploma program, you will work with model. Okay, so model actually are like our instruments to do experiments like this. Okay, so the only laboratory that we have is the Earth, and we cannot do nothing more. A little bit on that because we risk to degrade actually, we already did some experiment in our work, in our Earth system. Do you know why? Which was the biggest experiment, which was maybe not, at the beginning, human didn't think to make an experiment, but this is what exactly they did. So it's an experiment which started and still is working about 200 years ago. Industrialization, you're right. So with the industrialization, we make an experiment actually, and we are measuring the effect of that experiment. Because even if people were a little bit unaware of that, they just started to change the chemical composition of our Earth system. So it was an experiment, not very, let's say, thought, because maybe people were, well, we cannot say. No. But there were also other experiments. For example, in the ancient Roman period, when the Roman Empire failed and totally collapsed about the 4th or 5th century after the birth of Christus. So all the northern Africa was cultivated by with crops, okay, and of course after when the Roman Empire collapsed, all the big the landlords, let's say, the owner of these vast areas of grain, because that was the let's say the storage of the grain for the rest of the empire, they collapsed. And so if you take more or less the northern part of Africa with Tunisia and Libya and Algeria and Morocco and Egypt, so all this part here, more or less, with the Nilus here, was completely or almost fully covered by grain. Okay, big grain fields. So with the collapse of the Roman Empire, all these areas completely changed, and people use it to change from agriculture based on vast land cultivated by grain, with sheep sheep farms. Okay. And you know that sheep tends to take the grass and doesn't leave nothing, okay? Because they completely change, differently from cows, which grab the grass, but the roots of the grass remain. The sheep completely take. And so in, I don't know, maybe a couple of centuries, all these areas completely changed. So the albedo of this area completely changed. So the reflection of the energy from the sun in this area completely changed. So someone think, of course we do not have any kind of measurement of that period, but from the past proxies related to pollen, to literature also, people understood or had an idea that the climate of the Mediterranean basin were completely different. Okay? So that was the first experiment. There were many of them, more local. Of course, the one with the industrialization was global. Okay, so climate is another topic, but now we want to, in the last, let's say, 10 years, the study of the Earth system was become even more multidisciplinary. Okay, so we don't have just atmospheric processes or ocean processes, but we have also ecosystem processes. Okay, and so climate models must include not just the blue part related to atmosphere and ocean in particular, but also the ecosystem part, because for example, the effect of chlorophyll and of the organism within the ocean is very important to the chemistry of the entire Earth system. Okay, so half of the oxygen is produced in the ocean, and I think 80% of the CO2 produced by human since the beginning of the industrialization was actually stored from the ocean. Okay, so ocean is 70% of the surface, so it's a big heat storage for our Earth. But of course, geophysical fluid dynamics doesn't study only Earth, because if you take a planet which rotates, you know very well, and if you study the fluids flowing on this planet, of course, you can also make GFD on this planet. Like, for example, here there was recently a couple of very beautiful missions of NASA on Jupiter and on Saturn, which gave us the opportunity to change completely the idea that we had of this planet, which was related to picture like this. Okay, so this was 2000. Spacecraft Cassini. This was 17. Spacecraft Juno spacecraft mission. Okay, so all these phenomena here, okay, can be related, can be explained, can be described mathematically with GFD. Okay? And this is a picture of the Saturn North Polar Hexagon. So it's incredible if you see here the rings of Saturn, and here a sort of almost perfect hexagon which was kept by the spacecraft. Okay, so you can find a lot of very beautiful images on the NASA website. Okay, so we almost try to answer to the first question. So why we are studying GFD? Any idea? From the past? Come on, don't be shy.
We want to understand the fluid dynamics in the Earth and to try to predict what is coming next.
Perfect, exactly. This was one of the ideas. And if you go in the past, you will find in many poems, in many literature, that people, well, humans have been always fascinated about fluids. Okay, so if you think about the ocean, if you think about the atmospheric processes, if you think about the waves, so you can see that most of them were actually taken and became subject of very important pictures. So this is Leonardo Da Vinci, which was one of the first who tried to mathematically describe the fluid flows, especially the turbulence. This is a very famous paint by Hokusai, the Great Wave, a Japan painter. This is another painter of William Turner from the Gothic period, where the snowstorm over Hannibal. Hannibal who crossed the Alps with his army from Africa to invade Rome. And finally, another more recent from William Homer, the Gulf Stream. So this is the idea of the Gulf Stream. So a man in a very small boat surrounded by sharks with the big waves and something like cyclones or hurricane, yeah, exactly. Okay, so hurricane, for example, you know which is the origin of the name hurricane? Huracan. It was a god. Okay, in the Caribbean culture, Huracan was the name of the god who was, of course, the god who divested and created a big mess. Okay, so curiosity, fascination. The second thing is very similar to what Meleze said. Okay, so the possibility to predict. So we have here some picture of very strong tropical cycle over Cuba, which knows very well about cyclones. Then we have other sea sprout or even funnels over the ocean. These are another funnel. This is prediction of the NOAA for the, which was that? I think tornado prediction. And also there should be, okay, no, yes. Okay, what you, oh no, that was another presentation. And something which is now very interesting, which still make use of GFD, is the possibility to produce energy. So this is something that, if you think, always was part of our culture, because if you think about mills were very common in China, very common in Europe, both using the force of the water and the force of the wind. Okay, so now these are like very modern mills, and we are working. There are a lot of people and a lot of investment on this kind of wind farm in the ocean, or this which looks a little bit more futuristic. And some says that the wind could supply up to 20% of global energy, electricity by 2030. So this was 2014. I started to put this slide, I think 4 years ago. So I hope to reach 2030 to see, okay, we were there, right or not? Okay, so still 12 years. Okay, what we are also doing with GFD, we are also trying to monitor what happened in our system. So this was land and ocean temperature percentile between January and December 2015, which was one of the warmest years in the, let's say, record period. So you can see that the record warmest, so the darkest red color, was very, very spread in a lot of areas. So in the Indian Ocean, Europe, Southern Europe, Northern Europe, Central Europe, Northern Europe, most of the Pacific, Northern South America, South Africa, you know that, and also here, Siberia. So I'm not here to talk about climate, but just to give you an idea that this is a production, of course, of measurements. Okay, so people measured the temperature in most of these. Let's say we can measure the temperature. We will see in a few minutes from the satellite, of course. But if there are cloud cover, we have to deal with some other instrumentation. This is the very last product. So the first one was made by NOAA. Okay. So the National Ocean and Atmosphere Administration from US. This was a very recent product by Copernicus. Okay, so this is the program I told you before. So Copernicus is, in this case, this is the service related to climate change, which is organized and led by SEMWF, which is the European Center for medium weather forecast. And again, you can see here a very surface air temperature anomaly for October 2018 relative to this period. So looks like a little bit less worse than what we saw before, but not enough. This is all this area of the western North Siberia is very high. Also this area of Northern Africa, and this area also here. You know that South Africa is still suffering from a very, very big problem with the drought. And also California, southern eastern US, most of the South America, Australia, and also all this area of the Antarctica. While we have a few areas which look at the cooler than the average, which is this area here, Northern America and Greenland. But this is just 1 month, okay? So at the end of the year, so in 2 months, we will have a new plot like the before, like that one before. But since now, yes, please, John, come on. We were waiting for you.
I'm ready.
It's okay.
Yes, sorry.
It's okay. It's okay. You have some. Sorry, John. Your experience is mathematics, meteorology.
Mathematics and physics.
Mathematics and physics. Okay. Okay, and this is a very small snapshot on the Europe, and you can see that most of Europe practically experienced October, which was warmest. But maybe one of the most urgent problem that we are going now is related to all the problems, all the effects related to climate change and effects of climate change on the coastal areas. So you can have like storm surge or sea level rise. And also all the problems related to the transportation. So things like this can happen and happen very, very often because the transportation by sea has increased a lot in the last 10 years. And of course, incidents like this happened as well. And so GFD can be useful also to try to predict and to give to big tankers like this the best route in order to avoid harsh conditions in the sea. And one of the worst problems that we are going to face is the pollution, and in particular related to plastic. Okay, so plastic is has now become a very strong problem. Plastic has, I mean, it was like started to be created about 50 years ago, 60 years ago, okay, in the 50s. So before, plastic simply didn't exist. And now we have very, very worrying thing, the fact that, for example, 52% of sea turtles worldwide have accidentally eaten plastic trash in the ocean. 50%. So one turtle over two ate plastic. 90% of seabirds eat plastic trash. So plastic is part of diet of the seabirds. 20% of fish found during one expedition had the plastic in their stomach. So we produced plastic, we used plastic, and we actually are eating plastic. Because if we eat fish, plastic are going to become very, very small, and at the end of the food chain, it will arrive to us. Even if we decide not to eat fish, okay? But this is another problem. So there are a lot of information on plastic, and yes. So if you go on Google Trends and you put plastic in the ocean, plastic sea, you will find that from 2013, the interest over time has increased a lot, especially in the last year, okay? So this was done thanks to research. So thanks to people who actually studied and started to study, like you, GFD, fluid dynamics, meteorology, oceanography, earth science, solid earth, of course, also, even if solid earth is a little bit different, okay? So it deals with different ages, but still, also solid earth is very important. And actually, GFD is also very important to study the interior of the earth because of the plasma effect. I would like to take some breath just after, yes, like after half of the lesson, just to give you, this is a trailer of a movie which it's a documentary from 2016.
I remember the first time I saw a blue whale. Oh, look. I followed them since childhood. What do you think it's from? Is it from a ship? I could see plastic everywhere. We were in what we thought was a relatively pristine environment. I started to wonder what was happening in oceans elsewhere on the planet. Growing up, my world was the ocean. It's where I feel the most spiritual.
As a freediver, it was the place where I proved myself to myself. Finally, have the opportunity to pay the sea back.
Only a fraction of the plastic that we produce is recycled. This is never going to degrade. It's got nowhere to go. This is something that these animals, they were forced to endure because it was man-made and we put it into their environment.
The record is 276 pieces of plastic inside of one 90-day-old chick.
If the plastics are in the food chain for the dolphin, they're also in our food chain. Exactly.
Communities are built on these landfill sites. So sweet potatoes, corn, sugarcane, all growing on 40 years of garbage. Do you have anything not wrapped in plastic? No. No. We have to make our life better for our kids and children. Change is possible. It starts with us.
Okay. So I think it's possible to look at this documentary on the web, or very small. Okay, this is another story about another experience. Okay, so it's Plastic Ocean, this movie. So I think it's very inspirative. Okay, so you are the future actually, and you who are studying GFD, you are studying earth science in general, you can be part of this change, or this wave of change. Okay, so and especially those of you who are coming from the, let's say, developing countries, you are really the people where our planet is going to put their hands. Okay, so welcome and have a good work. Because it's a lot of work to do. So we have to clean what our fathers, I mean, not our fathers in personal father, but the people who were before us put in the ocean especially, but not just in the ocean, but also in the atmosphere. Okay, so third question is how? Okay, how do we study GFD? How do we study ocean? How do we study atmosphere? Any idea? Which are the instruments? Which are the approach? Come on. Be inspired.
Using mathematics?
Using mathematics, that's great. Something more?
Physical laws.
Sorry?
The physical
laws, okay. So I'd say equation, analytical aspect, approach. Other thing, how we study the environment. So this was something that was done since the beginning.
True observations.
Exactly, observation. And finally, one more. This is not very used, but it was used, especially more from the fluid dynamics. So it's something that we can do in a very simulation. Yes, we have two kinds of simulation, numerical simulation, but also laboratory. Okay, so physical laboratory. So very good. So these are some pictures taken from the web as well. So actually this is, I'm very proud to say that this is our research ship. So the research ship of the OGS, Explorer, which now is going to be retired because it's no longer able to, I mean, due to the law of the sea, is no longer able to go to the Antarctica and the Arctic, but made something like 11 expeditions to the Antarctic. And this is the castle of Miramar, of course, and this is another instrument of OGS. So OGS have a very strong experience in instrumentation, ocean instrumentation. This is a glider, okay? A glider is an autonomous vehicle which practically dive and, let's say, glide into the ocean. This is one picture taken from a typical research cruise. And this is a cartoon explaining the working of a float. Okay, floats are other instrumentation which are related to the satellites. So they were put in the ocean by ships. They drift at 1,000 meters, about 9 days. Then they goes deeper up to 2,000 meters. And when after, let's say, 5 or 10 days, according to the programmation, they go up to the surface. And when they go up, they take measurement of temperature, salinity, chemical substances. And when they are surfacing, their antenna is communicating with a satellite network called Argo. And so we can have, in near real time, information from this kind of element. There are about 4,000 of floats, Argo floats, in the global ocean actually. Okay, and they are really taking like sort of the fever, they measuring the fever of the ocean. Okay, because you know the temperature of the ocean is increasing as well as the air temperature. Okay. Atmosphere. So from atmosphere we have, of course, satellite, which are also used for the ocean. We have experimental airplane. We have a small van with all the instrumentation. This is from the National Silverstone Laboratory of the NOAA. And then we have the balloon, the radio sound balloon, which are released every 6 hours at the same moment in all the Earth. Those who study meteorology know that. So in all the station of the Earth, the closest to ours is in Udine, about 1 hour from here. So every 00, every 6, every 12, every 18 UTC. In all the world there are men like this one who release this balloon, and this balloon take the profile of the air. Exactly how done by the float. Okay, so profiles, vertical profile. Yes, please. Yes, if you have questions, just stop me. Yes.
I was only wondering. Nowadays we have drones which are really cheaper. So instead of, why do we always fly balloons on drones?
It's a good question. I don't know actually. I don't know if someone has already used drones to take measurements. I think it's possible. The problem is that with drones, maybe you are going to, it's not easy to relate, for example, the measure of the wind with the velocity of the drone. So you can have two different velocity, two different parameters to take in account. The other important aspect is that this kind of instruments are standardized. So it's about maybe the Water Meteorological Organization, it's I think 70 or 60 years that constantly keep the same standard for this kind of instruments. Maybe drone will be the future. I'm pretty sure about that. But it will take a little bit of some years to create a standardization for the instrumentation. Because if I want to measure the temperature of the air, I want that measure will be the same if I am in Italy or in Ghana or in Nepal or in Ecuador or whatever. Okay. So what I'm measuring, the sensor that I'm using should be fully standardized. Otherwise, I risk to include some error. And uncertainty and error, since all these data, so this is a picture of all the global observation systems, so where you have from ships and satellite and radio sound and aircraft and so on. So all the data that are captured by here, basically this is another one, a fixed mooring which is in front of Castle Miramare. So all these data are standardized, quality controlled, and then are used to be inserted within the models. Okay, because the model for the weather forecast and for the ocean forecast are, let's say, kicked a little bit by this data through a process which is called data assimilation. Okay, so data assimilation is a mathematical approach which was invented, that's formalized in the 70s and became, now it's practically a standard in the forecast, and is strongly based on mathematics, and is able to create a sort of, let's say, the best estimate of the initial condition for a model, okay? Because it's very important, and in order to avoid that uncertainty within the model will spread and will propagate in order to make the forecast worse than with the data assimilation. So indeed, when you look at the quality of the weather forecast, I mean the performance, the skill of the weather forecast, you can see that the best forecast you have after 3 days, in the first 1, 2, and 3 days, and after the third days, the performance starts to decrease. Okay, last is the laboratory. Okay, this is a picture taken from the University of Naples with the naval tank. And also, as you said correctly, the mathematical approach. So working with the analytics, working with the mathematics. And of course, we can put all the mathematics. This is the Navier-Stokes equation that you already knew. So this is the real start of the course to use this the equation and to be solved by very big machine. You know where is this machine? Can you grasp where is? It's not easy, but if you are very good, maybe not in this picture. Okay, these are Chinese characters. Okay, so actually the most powerful computers are in China. Okay, so this was only in the last 5 years, because before US was like the first, of course, having the most powerful computers, but now China is going to become even more powerful from this aspect. So okay, this was a nice picture of a visit of ex-former President Obama at MIT, and I like it very much. Just to close this section, to say that Moses said, and these are the two equations of Navier-Stokes and the Waters pattern. Okay, so just to say that, of course, never forget that mathematics is at the base, okay, of all the GFD and, of course, fluid dynamics that we are going to work with. Okay, so just to recap, geophysical, two important effects also for you who arrived later. So rotation and stratification. Why fluid? Because we are working on gas, atmosphere, and liquid ocean. Why dynamics? Because we are interested to study the evolution of fluid under the influence of body forces, gravity, and surface forces like friction, like wind, for example. So GFD treats the physical aspects of the dynamics of fluids on Earth-like planets. So not just Earth, but also other rotating planets. Then we are interested to large-scale motions. And another interesting character of GFD phenomena is the similarity. Okay, so similarity among different systems. So you saw, let's say, cyclone-like phenomena on the picture of Jupiter, which are ruled by the same equation that rules on the Earth, of course. So what does GFD deal with? Atmosphere variability, weather and climate, ocean variability, waves, eddies, currents, but also the dynamo effect in the Earth interior, vortices on other planets, convection in stars. So not just Earth fluid dynamics, GFD, but also, let's say, planet fluid dynamics. Why study for GFD? Important for life, saving people, of course, because, for example, the forecast of hurricane contributed to save people, for the nature, of course, and for the energy. How to tackle with GFD? Observation, mathematical physical description of phenomena by means of analytical theory, numerical models, laboratory experiment. So all of these approaches, the mathematical ones, the numerical ones, and the laboratory ones, always have to be compared with measurement. So, okay, if I want to create a new theory, I have to compare it with the measurement. If I want to do a new model, don't do it, because it's extremely, use the model which are already present. But if I make a change in the model in a subroutine, for example, I have to compare it with measurement. Okay, so always and find the errors and quantify the error. Okay, one last point. If you like if you like numerical models, you have to consider also some related technological challenges. So HPC, the fast development of high-performance computing, big data, and the energy efficiency. Okay, so this is a picture taken from a paper on Science 2011, which tells you the increase of data coming from model in the yellow, satellite or radar in blue, and in situ or other. In situ means local, so like the floats, for example, or the mooring, the fixed mooring. Okay. So, and if you see here, this is in petabytes. So, starting from 2010 to 2030, you can see how the increase of data from models and from satellite is planned to be. Okay, so strong increase, which will create also new work, new jobs for people who will work only to analyze data. Okay, because we are going to have a lot of data. A lot of data. There are experiments, numerical experiments, made by very large groups of scientists. Each group has, let's say, uses a specific climate model, and they want to compare all the models. Okay, these are. There is an initiative called CMIP, which I think now it's at the 6th edition. Okay, so it's Climate Model Intercomparison Project. Okay, so if you Google, you will find a lot of information about that. And also, not just problem with the development of technology, but also development of algorithms related to the analytics of data, and also related to energy efficiency. Okay, don't forget it. Don't forget it, because it's very important, because we are used to talk about flops, floating point operation per second, but now we are going to talk about IOPS, so input-output operation per second. Okay? Because today, HPC is going to evolve towards a data-centric. Okay? So we are going to create a lot of data. We will have a big hub, big server with a lot of data storage, and our scientific computing will need data accessibility rather than computing speed, plus energy sustainability. Why? Because if you compute one calculation, this is about 1 picojoule, but if you move one calculation, this is 100 picojoule. Okay? So think about, do you as much calculation you want, but when you have to move, be careful. Okay? So that's why now people try to concentrate on very limited, spatially, geographically, data server about the amount of data, and give and allows researcher to access remotely to this data without bringing the data locally. Okay? If I am in Cuba or in Nepal, I don't want to spend a lot of money to have a data server in order to store a lot of data, but I want just to study, to make analysis on a database which is in some other place, and I have to be confident about that, and I can make all the analysis on my laptop, but just with not transferring all the data. Okay. Okay. So first definition of the day is scales of motion. So scales of motion, we already had an idea at the beginning when we talk about we look at the picture from the satellite and related to the circulation of the atmosphere and related to the ocean circulation. So scales of motion are defined as dimensional quantities which express the overall magnitude of the variable under consideration, and in some sense are some estimates or order of magnitude. Okay? So this can be done for this can be done for space. We use L. Time, we use T. So we use always capital letter. Velocity, we use U. Density, rho 0. Density perturbation or density variation, delta rho. And height, okay? Height of the phenomenon. So if we have, for example, a hurricane like this one, this was Hurricane Frances, September 2004. So these figures say that the diameter of the storm is about 800 kilometers with the top wind speed about 200 kilometers per hour, okay? So we can represent, without reading this one, okay, so the diameter is like this one. If you take the inner part, we have that the length dimension cover about 3 degrees of latitude. So we have that L is about 300 kilometers. The time scale is about 2 days. And the velocity is about 70 kilometers per hour. Okay, so this is maximum. These are the maximum scales, and these are, let's say, the minimum scale. Okay, so we can constrain every kind of phenomena within this kind of scales. Okay, so scales of motion are extremely important, and it's not so easy to select them. It's more, let's say, an art than than a practice, and it comes from practice, actually. Okay, so you have to study a lot of phenomena and to understand which is the correct scales of motion that have to be applied to this phenomena. And why scales of motion are important? Because as we introduced at the beginning, we want to know at which scales the ambient rotation becomes an important factor in controlling the fluid motion. Okay? And the second question is at which conditions stratification effect have a dynamic role on fluid dynamics. So we saw at the beginning the picture of the drop of water, and we were quite confident to say that that was not affected by rotation. Okay, but we can, in any case, represent and try to quantify a little bit more the scales. So, first of all, we want to define the ambient rotation. Okay? So what is the ambient rotation? This is the rotation of the planet Earth. Easy. Okay? So we call it with capital omega. And this will be 2 pi over 24 hours plus 2 pi over 1 year. Okay, easy. So this is the velocity, the rotating velocity of our planet. So one rotation every 24 hours and one larger, slowest rotation every year. Okay, one rotation around its axis and one rotation around the sun. So we can call it write this like TR. Of course, this is much more important if you make the calculation. And this is the time scale of rotation, okay, which characterizes our planet. Of course, other planets will have other time scale of rotation. So if we calculate, this is about the first half is 7.27, the second is 0.02, 10 to the minus 5, second to the minus 1, which is 7.29. Okay? So, this is the first number that you must put in your mind, because I always ask this at the exam, okay? So never forget, because it's important. I mean, you don't have to study by heart, of course, but there are some scales, some numbers, some constant. This is not a constant, of course, but which must be part of your background, okay? And every time I say that, because from the past exam, there were some students who didn't know. So it's important, very important for you, first of all. Okay, so now we can define capital T, as we said before, as the motion time scale. So, and we define a dimensional number. We will see that a dimensional number will be very important in GFD, which is defined as the time of rotation, ambient rotation, over the motion time scale. Okay, so omega is a ratio between two time scales. Okay, so it's a dimensional number, doesn't have any unit of measure. So this will be PR over T, or also 2 pi over capital omega over capital T, or 2 pi over capital omega capital T. Okay? So, if you remember from the beginning when we talk about the drop, we can say that only when T is larger than TR, which means omega smaller than 1, we can say that the ambient rotation becomes an important factor in controlling the fluid motion. So only when our motion, our time scale motion, is longer than, let's say, about 24 hours, because, of course, this is much larger, like a scale, we will have that the rotation is important. So we can do something similar if we consider not just the motion time scale, but the time related to, let's say, cover one distance L at velocity u. Okay, so this was like sort of local scale. Okay, so we are going to measure the time scale of a phenomenon looking at that phenomenon. Okay, here we are following the fluid. Okay, the fluid parcel, and the fluid parcel has a velocity and travels over a length L. So we can say that, of course, the velocity scales are related to length over time scale. Easy, okay? So it means that T, will be L over U. Okay? So the time scale related to the motion of the parcel, rather than keep just considering the phenomena, look at it whole. So for example, in the case of the hurricane, this is like the total time scales, the 2 days, okay? And this is related to the time scale related to the velocity of wind, okay? So how long is the distance covered by a parcel during the motion of the cycle. So we can define a new, another dimensional number, which we call it epsilon, which again is the time of rotation, tr, over the time taken to travel L with the u velocity, which is L over u. Okay? So this is again 2 pi over omega. And so we will have 2 pi u over L omega. Okay? So these are, if you even do not consider the numerical factor, so we have two-dimensional number which takes in account the ratio between the time scale of the phenomena we are going to study and the time scale related to the velocity, so to the dynamical aspect of this phenomena. And also, like in the other case, in the previous case, our question relating which scales of the ambient rotation becomes an important factor in controlling fluid motion, we will have that epsilon must be smaller than 1. Okay?
Sorry. What do you mean by the time scale of the hurricane is 2 days? That means it takes 2 days to complete one rotation?
No, it takes 2 days to travel from, for example, Cuba to Florida. Okay, because if you take the rotation is much faster, because the rotation of a parcel with a wind of about let's say 100 kilometers per hour is you can take make the counts and it's much smaller. Okay, but still is important. Okay, so it means that if epsilon is smaller than 1, we can have that L over U, of course, is larger of 2 pi over sigma. Okay? So we can try to take some examples, and from this, since this is equal to TR, we can say that given L, U will be smaller to L over TR to feel the effect of the rotation. Okay? So, with the scales going by 1 meters to the Earth radius, you can see that the velocity actually increase, but the limit is related to this, let's say it's a first approximation, okay, so keep it like it is. It's a very, very broad consideration that we are making. So we are going to very, very small velocity, slow velocity, to velocity related to typical velocity of wind, like this one, so tenths of meter per second, or of ocean current, this one, okay? So this means that these are the typical velocity of wind, so it means that the typical atmospheric phenomena will have dimension order of 1,000 kilometers, okay? While if this is the typical velocity of the ocean current, the typical ocean phenomena will have dimension of 100 kilometers, which is something that we already saw from the two pictures at the beginning, okay? So phenomena in the ocean tends to be shorter and slower than phenomena, shorter and slower than phenomena in the atmosphere. Yeah?
How different is the omega and the epsilon? Because they are all having the denominator equal to t. And from here, t equals to L over u.
Yes. So The difference is related to the fact that this doesn't take in account anything about velocity and length. So this is just related to time. Okay, so I'm just looking at the phenomena from its time scale, how the phenomena is progressing in time without any characterization of the dynamics of the phenomena. Okay, just looking at the time scale. For example, a weather phenomenon. So thunderstorm, for example, which is related to fronts. So fronts of like that we are having today, it is about 1 day. So if we stay here in Trieste and we measure the time related to the expiration of the weather phenomena, it will take about 1 day, 2 days. Okay? But if we go in the front and we measure the velocity of the front, it may be different. Okay? So in that case, we not just stand like in an Eulerian frame, maybe you know that, but we follow the system in what we call Lagrangian frame. Okay? So following the system, we are able to also understand the velocity and the distance which cover. I can understand that from a mathematical point of view, this is exactly the same. But we will see later that there is a very specific distinction among these two, between these two. Okay?
Sure. You said that the atmospheric motions or phenomena are slow and.
No, I said the contrary. Sorry, maybe I
the ocean. You said they are short. Sorry.
Yes, ocean phenomena are shorter and slower than atmospheric phenomena that are longer and faster. Sorry, maybe if I said the contrary. Okay. So eddies, for example, travel slower than cyclone. Okay, and of course this is related to what, according to you? Which is the big difference between
the viscosity?
Not just the viscosity, but not just that. There is one more important quantity that differentiate atmosphere and ocean. Yes, density. It's one. There are 3 orders of magnitude between ocean and and atmosphere. Okay, so sometimes it's very obvious, but this is actually at the base of it. Okay, so we can do something similar also for stratification. So in order to answer to the other question related to which are the scales where stratification start to be considered. So let's think to take a column of fluid, no matter if atmosphere or ocean. So we can consider a reference 0 here in the height scale capital H. So we can be in the ocean or in the atmosphere. And so we can take, let's think that this is a stratified flow, okay, fluid, sorry. So we have, at this reference, we will have that the density is described by a quantity ρ0, okay, a background density, plus a variation, delta ρ, which is positive. And here is a little bit lighter, okay? So the idea is to move this parcel from here and rise it here, okay? So there is some force, of course, which takes the parcel from here and raises it from here. So this means that after a while, we will have ρ0 plus delta ρ here and ρ0 here, okay? So this is the initial condition and this is the final condition. So if we want to calculate the variation in the potential energy per unit of mass, This is nothing more than the difference between the final state and the initial state. So the final state, we will have rho 0 plus delta rho GH. Okay, this is the usual form for the potential energy, plus rho 0 multiplied by 0, because it's here, minus, we have rho 0 GH plus rho 0 plus delta rho G multiplied by 0. Okay? So, this is nothing. We can neglect this to this. And so, we have that the variation of potential density is nothing more than the variation is related to the variation of density multiplied by the entire height. So this is the perturbation that was made to our system to transform it from this part to this part. So, at the same, we can consider also the kinetic energy. Per unit mass. So, kinetic energy is simply the multiplication of the background density multiplied by the square for the velocity. So, think that there was some sort of motion in the background that was able to transform, to take this parcel from here to here, okay? Some sort of, we will call it mixing, okay? Okay, now, again, let's define a dimensional number, which we call it sigma for now, and, sorry, there's 1/2 here. So it's practically the ratio between the kinetic energy and the potential energy. So we can have 3 different cases. We can have that sigma is order of 1, sigma may be much smaller than 1, or sigma much larger than 1. Okay? So in the first case, we have that the kinetic energy and the potential density variation are of the same order. Okay? So it means that if I change a little bit the potential energy, it will change also the kinetic energy. Okay? Because this must be maintained at the same order. So it means that actually stratification have an effect on the dynamics of the motion, of the flow. In the second case, when the kinetic energy is very small with respect to the perturbation of potential energy, again, if we have a change in the potential energy, it will have an effect on the kinetic energy. Because again, if I change a little bit of this, this will be also extremely, it will have an effect on the kinetic of the system. In the third case, on the contrary, the kinetic energy is so large with respect to the density variation that if I change the density, if I change the potential energy, the kinetic energy doesn't care. I mean, it is not affected. Okay? So when sigma is, let's say, order of 1 smaller or even smaller than 1, we can say that stratification can have an effect on the dynamics of the parts of the system. Okay? So as soon as the kinetic energy is not much larger than the potential energy, which means that actually when this goes to 0, it means that we have a homogeneous water-air column, fluid, let's say, fluid column. So when the variation in potential energy goes to 0, in any case, of course, the kinetic energy is not affected by any kind of stratification. Okay? As soon as this density variation, because these two, of course, can be, this is a constant, of course, and this can be considered as a parameter of the system. So when this change in comparison to what? To the velocity, okay, and of course of the background density, we can have that stratification start to be important in the system. Okay, we can take also the complete case, which is the most common. So the complete case will have epsilon order than 1 and sigma order than 1. So it means that rotation and stratification are equally important, which is the normal in GFD. So when epsilon is order than 1, if you remember how we defined epsilon, we have that L is order than 1, the U over omega, neglecting the factor 2 pi. And if sigma is order than 1, since sigma is also here neglecting the 1/2, so we have rho 0, U squared over delta rho G H. So when this is 1, we can extract them from here and solve this, finding U. So U will be 1 over rho 0. No, sorry. Delta rho over rho 0 GH. Okay? So we can solve this and put U here. And we will have a sort of a natural length scale for GFD phenomena. Okay? I'm just making very, very basic, very, let's say, intuitive consideration.
There's a 2 lambda.
Sorry, 2 lambda.
From the kinetic energy term.
Yeah, I just neglected. I neglected because it's just a number. I mean, if you want, you can put this 1/2 within, but it's just I'm interested more in the not just in the numerical factor. Of course, this is not an equal. This is order of. Even here, I have a 2 pi factor. Okay, so I can neglect the factor. Okay, so I'm not making exact analysis, but finding more the importance of the scales, of the order of magnitude.
And if I may ask, what is the value of the phi? The equation above?
The value of the
phi?
Ah, no, this is rho.
I mean, the equation above?
This one, no, this is 0. Sorry, because this was from 0 to h. Okay? Z equal to 0, Z equal to h. Stop me if you have, because sometimes my writing can be too fast, or sometimes I can forget some. Okay, so this is the definition of natural length scale, and if we recall the numbers, so omega is 7.29 10 to the minus 5 second minus 1. G is, how much is G? 9.81 meters squared per second. Okay, so now we can calculate this natural length scale, for atmosphere and for ocean. So for the atmosphere, we can take a background density of 1.2 kilogram per cubic meter. We can take a typical variation delta rho of density of 0.03, for example, kilogram cubic meter, and a typical height of 5,000 meters. So 5,000 meters is actually half of the troposphere. Okay, so these are the scale of motion of typical weather phenomena. Okay, density of the air, variation of density, and extension of where we can observe a variation of density. Okay. For the ocean, rho zero is 1,028 kilogram cubic meter. Delta rho is a little bit larger, 2 kilograms cubic meter, and H is 1,000 meters. So these are the typical scales for big ocean currents. Okay, so currents that have a vertical expansion up to 1,000 meters. Okay, something like the Gulf Stream, for example. Okay. Okay, so now if we calculate L, so for the atmosphere, you can do it by at home if you like. It will be about 500 kilometers, and the velocity will be about 30 meters per second. So I calculate L, and then I calculate U from here or from here. Okay. And for the ocean, L will be 60 kilometers, and U will be about 4 meters per second. Again, I'm using this symbol, okay? I'm not putting equal, okay? Because it's all orders of magnitude, okay? I can also write, say, O to the 10 to the third, O to the 10, O to the 10 to the second, and O to the 1. Okay? Kilometer, meter per second. Okay? So, as we saw at the beginning, there is one order of magnitude between the length scale and the time scale of the ocean and of the atmosphere. Okay? And this was only extracted from this very, very, very simple consideration. Okay? No equations, just using scales of motion. That's why I told you that scales of motion is extremely important, because then they will help us to make a lot of simplification. And I think there is one final slide. Give me a couple. So if we consider different phenomena in the atmosphere and the ocean, you will see length scale, velocity scale, time scale, and you can see that, for example, microturbulence, which is no longer than 1 meter, but is very, very fast, and has a very, very short time scale, cannot be considered as a phenomena for GFT. Same as microturbulence or internal waves, okay? But, no, I remember there was some sort of arrow, but okay, no problem. So mountain waves, which was the picture that we saw before, it's let's say on the border, but here they put it after the hurricane. Let's say also coastal upwelling, fronts, eddies, major current, and large-scale gyre. So we are going from let's say days, because you remember that GFD has the time scale larger or similar to 24 hours. So 1 day. So tornado are not subject of GFD strictly. Hurricanes are. Tides strictly are not subject of GFD, but of course they are part of currents. So we are a little bit, we have to be very careful, because of course when we work with the numerical models, we should put somewhere a sort of barrier, okay? We cannot, it's not possible, as you maybe know, to include microturbulence in a numerical model, especially global models. Absolutely unfeasible from the computational point of view. But we are going to, let's say, to push the computational efficiency to try to include a number of these phenomena within the systems, the models. Another interesting thing is that if I want to represent a typical phenomena in a model, so I must remember that the phenomena which has these typical scales are referred as mesoscale. Okay? So mesoscale phenomena are the cyclones, for example, in the atmosphere, and the eddies in the ocean. Okay? So a numerical model must be able to represent, or they should do their best to represent mesoscale. Okay? This means that the typical grid of a numerical model, you know that numerical model can be, I can discretize the equation, the Navier-Stokes equation, and put a value of temperature and velocity, for example, on the different vortex of a grid. So I need a finer grid to represent ocean mesoscale rather than atmosphere mesoscale. That's why ocean let's say operational oceanography, so ocean forecasts, are a little bit, let's say, late than atmosphere. So the technology related to atmosphere and the use of weather forecast has been much more advanced, because I may need grids which are, let's say, coarser than this one. Okay, so I can to represent correctly the eddies that you saw at the beginning, and this is a very, very important aspect. Okay. Yes. So we saw here that the phenomena were very, very large. Well, let's say larger than this one. Okay. So this is a model where you can allow eddies to be represented. So we can talk about eddy permitting ocean models. Okay. That's why global ocean models, it's much more difficult to build rather than global atmospheric model. Okay? That's why ocean modeling, in some sense, is some, let's say, years late in terms of technology, and needs a lot of more science and also computational power with respect to the atmosphere. So, to synthesize, ocean processes are caused by lateral boundaries that do not exist in atmosphere. Atmosphere motion are strongly dependent on moisture content that does not exist in the ocean. Atmosphere is thermodynamically driven, so the solar radiation is the main source of energy, while ocean is forced by different mechanisms: tides, wind stress, surface fluxes. Okay? So tides in atmosphere can quite well neglected. They exist, of course, because of course even air parcel has mass, so they can, but the effect on weather is practically negligible. While tides, especially in shallow area, like for example the Northern Adriatic Sea, or for example the Baltic Sea, or for example area close to the Micronesia, so where the topography, the bathymetry is very shallow, I also need to include tides within a model, which is not easy, cannot be easy, okay? So our ocean is forced by wind stress, which is atmosphere, but actually surface fluxes, which is actually a consequence of the solar radiation, okay? Well, I think we can close for today. And we'll continue tomorrow. Can you include your name, please? Thank you.
Is on me.